A distant star hides a secret planet in its blinding glare. For centuries, the only way we could find these alien worlds was by observing the subtle ways they influenced their sun, like watching a star wobble or dim from an unimaginable distance. But now, a revolutionary technology is changing everything. This is the story of extreme adaptive optics, a system so advanced it allows our telescopes to directly photograph exoplanets for the very first time. By the end of this journey, you will understand how we are building the ultimate cosmic camera to capture light from another Earth. We will uncover how engineers are overcoming a glare billions of times brighter than the target, and what these first pictures can actually reveal about conditions for life. What do you believe we will find when we finally see another world clearly? The heart of the challenge is a problem of cosmic proportions. Every star is a raging nuclear furnace, pouring out a flood of light that utterly drowns the faint, reflected glow of any orbiting worlds. The difference in brightness is not just large, it is almost incomprehensible. A typical star can be billions of times brighter than the planet we are trying to see. This creates a staggering contrast problem, like trying to spot a single, tiny firefly hovering right next to the blinding beam of a giant searchlight from miles away. But the difficulty does not end there. From our vantage point across the vast emptiness of space, that firefly and its searchlight appear incredibly close together. This is the challenge of angular separation. Even a planet orbiting at a comfortable distance from its sun is just a tiny fraction of a degree away in our sky. For the closest star systems, separating the 2 points of light requires a resolution finer than reading a newspaper from 50 miles away. For decades, these two immense hurdles, the overwhelming glare and the minuscule separation, made directly seeing an exoplanet seem like a fantasy. Our telescopes, no matter how powerful, saw only a single, brilliant point of light where an entire solar system existed. We knew the planets were there, but they remained hidden, their presence inferred from shadows and wobbles never seen. The question was not just about building a bigger telescope, but about teaching it to see in a whole new way. The solution to this cosmic vision problem arrived not in deep space, but in the turbulent ocean of air right above our heads. Our atmosphere, a protective blanket that makes life possible, is also a maddening obstacle for astronomers. It is a seething, turbulent fluid, with pockets of warm and cold air constantly swirling and distorting the light passing through. This is what makes stars twinkle, a beautiful sight that hides a frustrating reality for science. That twinkle is the image of a star being smeared, jittered, and blurred into a fuzzy mess. It is like trying to read a license plate from the bottom of a swimming pool while the water is churning. For the ultimate goal of spotting a faint planet nestled beside its star, this atmospheric blur was a deal breaker. You could build the most perfect, gigantic telescope on Earth, but its view would always be degraded, its potential resolution lost to the shimmering air. Something had to change, and it did, with a technology that gave our telescopes a pair of dynamic, self-correcting glasses. This is the magic of standard adaptive optics. The core idea is brilliantly simple. If you can measure how the atmosphere is distorting the light in real time, you can deform a mirror in the exact opposite way to cancel out the distortion. It is active noise cancellation, but for light waves. The system works by analyzing the light from a bright guide star, either a real one or an artificial star created by shining a powerful laser into the upper atmosphere. A sophisticated sensor watches how the image of this guide star is warped, and that information is fed hundreds or even thousands of times every second to a very special mirror. This is no ordinary piece of glass. It is a deformable mirror, a technological marvel whose surface is a mosaic of hundreds or even thousands of tiny, independently controlled actuators. These pistons push and pull on the back of the mirror's thin face sheet, bending its surface into precise, complex shapes. As the atmosphere blurs the starlight one way, the mirror deforms to unblur it the exact opposite way. The result is transformative. In an instant, the twinkling stops. The fuzzy blob of a star snaps into a razor-sharp, steady point of light. This correction unlocked the true power of the world's largest ground-based telescopes, allowing them to see with a clarity that once was only possible from space. It was a monumental achievement, a revolution in astronomical observation. But for the dream of directly imaging an exoplanet, it was only the first crucial step. Standard adaptive optics had given us steady stars, but the planet hiding in that glare was still billions of times fainter, a ghost in the machine that required an even more extreme form of vision. Yet for all its power, standard adaptive optics was only the beginning. To actually pull a planet from the stellar glare, we needed to push this technology into an entirely new regime. We needed to move from adaptive optics to what engineers call extreme adaptive optics. This is not a simple upgrade, it is a quantum leap in precision and speed, transforming a powerful tool into an almost unimaginably sensitive instrument. Think of the difference between a steady hand and a surgeon's hand performing microsurgery. The core components are pushed to their physical limits, where a standard system might use a deformable mirror with a few hundred actuators. An extreme system employs thousands, even tens of thousands of these tiny pistons. This creates a surface that can be bent and shaped with microscopic fidelity, correcting for distortions far finer than ever before. But a perfect mirror is useless without a perfect sense of the chaos it must correct. This is where the speed comes in. The atmosphere does not just distort light, it does so in a frantic, ever-changing dance. To keep up, the cameras in an extreme adaptive optics system do not just watch the guide star, they stare at it, measuring the wavefront of light thousands of times every single second. This incredible speed allows the system to react to the atmosphere's turbulence almost instantaneously, freezing the distortion in time and commanding the mirror to counter it before the next wave of light even arrives. The result is a level of stability that was once the stuff of dreams. The star's image becomes not just a steady point but a profoundly quiet and stable one. This supreme stillness is the final, essential ingredient. It is only when the star's light is rendered so perfectly motionless and calm that the billion times fainter whisper of a planet can finally begin to emerge from the shadows. At the core of this incredible system lies a piece of technology that feels almost like science fiction, a deformable mirror. This is not a simple sheet of glass. Imagine a mirror whose surface is a mosaic of hundreds, even thousands of tiny, individual pistons, each one smaller than a pencil eraser. These are the actuators, and they are the heart of the entire operation. Each one is connected to the back of an incredibly thin and flexible mirror face. Working in concert, these actuators can push and pull with microscopic precision, physically bending the mirror's surface into complex, contorted shapes. Their sole purpose is to fight chaos with calculated perfection. As the turbulent atmosphere scrambles the incoming starlight, the system calculates the exact opposite distortion needed to cancel it out. Then, in a fraction of a millisecond, it commands the actuators to bend the mirror into that precise shape. The distorted light wave hits this intentionally warped surface and bounces off perfectly corrected, as if the atmosphere was never there at all. This creates what astronomers call a flat wavefront, a perfectly organized plane of light that allows a telescope to see with its theoretical maximum sharpness. It is the ultimate clear sky view, achieved not by waiting for a calm night, but by creating one artificially, thousands of times every second. This relentless, high-speed dance of correction is what carves a zone of profound stillness around the star, finally allowing the faintest of cosmic whispers to be heard. But a mirror that can bend to any shape is useless without a set of eyes to guide it. This is the role of the wavefront sensor, the other half of the brain behind this cosmic vision. It acts as the system's hyper-attentive lookout, constantly scanning the starlight to diagnose the atmosphere's chaos in real time. One of the most common and brilliant designs is called the Shack-Hartman sensor. Its method is both simple and ingenious. Picture this device placing a tiny honeycomb of small lenses right in the path of the incoming, distorted starlight. This lenslet array acts like a vast compound eye, slicing the single, blurry wavefront into hundreds or even thousands of individual, smaller beams. Each of these tiny beams is then focused down to a minute spot of light on a super-fast camera sensor. Now here is the critical part. When the starlight is perfectly flat and undistorted, all of these spots will land in a perfectly neat, grid-like formation. But when the atmosphere churns, it warps the wavefront, causing some parts of the light to arrive slightly sooner or later than others. This means that the tiny beams, as they pass through the lenslet array, will be subtly steered off course. Their focused spots will not land in their assigned places on the grid. They will be displaced, shifted slightly from their perfect, calm sky positions. The wavefront sensor's camera captures this entire pattern of shifts hundreds or even thousands of times every second. A powerful computer then analyzes this map of misplaced dots. The precise amount and direction of each spot's displacement tells the system exactly how the atmosphere is bending the light at that very instant. It is like reading the ripples on a pond to understand the wind that is causing them. This torrent of data, a constant high-speed diagnosis of the atmosphere's turmoil, is what gives the deformable mirror its instructions. The sensor sees the flaw, and the mirror instantly sculpts itself to erase it. This relentless cycle of measurement and correction is what carves a zone of profound stillness from the chaos, a necessary silence in which the faintest of planetary signals can finally be heard. This entire high-speed dance between sensor and mirror hinges on one of the most formidable challenges of all, the need for instantaneous calculation. The atmosphere's turbulence changes so rapidly that the window for a perfect correction is breathtakingly short, measured in mere milliseconds or even microseconds. That is 1/1,000,000th of a second. This creates a punishing deadline for the system's brain, the computer that must take the wave-front sensor's data, calculate the exact mirror shape needed, and fire the commands to thousands of actuators before the atmospheric conditions have already changed. It is a relentless, high-speed feedback loop where any delay renders the entire correction obsolete. Think of trying to steady a friend's wildly shaking hand by watching its movements and giving instructions, but you must see the shake, process it, and shout a correction all within the blink of an eye. Now make that blink 1,000 times faster. That is the computational nightmare engineers had to solve. To meet this demand, they cannot rely on ordinary computers. These systems require specialized, real-time computing hardware, often built with powerful graphics processing units and custom-designed electronics that are engineered for one single purpose: raw speed. They are the unsung heroes of the entire operation, the hyper-fast nervous system that connects the observant eyes to the nimble hands. But even the fastest hardware is useless without the right instructions. This is where the algorithms come in, the sophisticated mathematical recipes that translate a map of dancing light spots into a perfect counter-distortion. These algorithms must be incredibly efficient, solving complex matrix algebra problems thousands of times per second. Every microsecond they save is a microsecond of atmospheric turbulence that can be cancelled out, carving a deeper and more profound stillness around the star. This computational ballet, performed at the very edge of what is physically possible, is what ultimately makes the faint, impossible glow of another world begin to materialize from the void. Even with a perfectly still star, that billion-to-one glare remains an almost impenetrable wall. To finally see the planet, we must not just calm the star's light, but physically suppress it. This is the job of the coronagraph, a brilliantly simple yet profoundly complex instrument that acts as an artificial eclipse maker right inside the telescope. Its name comes from the corona, the sun's faint outer atmosphere, which we can only see during a natural total eclipse when the moon blocks the sun's blinding disk. A coronagraph does exactly that, but for stars light years away. It uses a series of precisely engineered masks and filters to block the central, overwhelmingly bright light of the host star. Think of it as a tiny, programmable shadow, carefully placed just at the focal point where the star's image forms. By casting this perfect shadow, it dims the star's brilliance by factors of millions or even billions, carving out a dark zone in the immediate surroundings. It is within this artificially created darkness that the faint, reflected gleam of an orbiting planet, once completely drowned out, can finally emerge and be registered by our cameras. The coronagraph does not enhance the planet's light. It performs the equally vital task of removing the one thing that was hiding it all along. But creating this perfect shadow is an optical challenge of the highest order. Starlight is a tricky thing to contain. It diffracts and scatters around the edges of any mask, threatening to flood the dark zone with unwanted glare. This is where the coronagraph's design becomes a work of art. One of the most elegant and powerful designs is known as the vortex coronagraph. Instead of a simple opaque spot, it uses a special spiral-shaped mask, a piece of glass etched with microscopic grooves that resemble a whirlpool or a spiral staircase. When the concentrated starlight hits this spiral pattern, something remarkable happens. The light itself is twisted like water swirling down a drain. The waves of light are manipulated so that they interfere with themselves, canceling each other out perfectly in the center of the image. This creates a profound and deep null, a tiny, dark hole in the stellar brilliance where the planet can reside. It is a shadow created not by blocking, but by bending light against itself in a precise dance of wave cancellation. The combination is what makes direct imaging possible. The extreme adaptive optics system delivers a perfectly steady, sharp image of the star, and the coronagraph then reaches in and digitally turns that star almost completely off. For the first time, we are not just inferring a world's presence, we are gathering its actual photons, the very particles of light that have traveled across the galaxy after bouncing off its surface or filtering through its atmosphere. What secrets might those few precious photons hold? These two instruments, GPI and Sphere, became the vanguards of this new era, the first great observatories dedicated to hunting planets by sight. Perched under the pristine skies of the Chilean Andes on neighboring mountaintops, they took the principles of extreme adaptive optics and forged them into complete, dedicated planet hunting machines. While they share a common, revolutionary goal, their designs reflect two distinct philosophies, two different approaches to solving the same monumental puzzle. The Gemini Planet Imager, or GPI, was designed from the ground up as an integrated system. Its power lies in its holistic harmony, where every component, from its advanced deformable mirror to its sophisticated coronagraph, is engineered to work in perfect, seamless concert. This allows GPI to create an exceptionally stable and dark region around a star, a perfect observational bubble for spotting young, bright, massive planets. Its specialty is the giants of other solar systems, worlds like Beta Pictoris b, a planet it captured in stunning detail. This is a colossal world, several times the mass of Jupiter, orbiting a very young star. GPI did not just see a dot of light, it took a series of images that actually showed the planet moving along its orbit, a time lapse of another world's year. This was a direct confirmation of orbital motion, a cinematic view of celestial mechanics playing out light years away. On the other arm of the mountain, the Very Large Telescope hosts its own champion, an instrument with the fittingly grand name of Sphere. Sphere name reveals its own unique strength. The spectropolarimetric part means it not only blocks starlight to take pictures, but it then dissects the faint remaining light with incredible precision. It acts like a cosmic prism, splitting the planet's gleam into a rainbow of colors, a spectrum. This spectrum is a treasure trove of information, a chemical fingerprint that can reveal the composition of the planet's atmosphere, whether it contains gases like methane or water vapor, and even the size of the dust grains in its clouds. Sphere also uses polarimetry, studying how the planet's light waves are oriented. This is particularly powerful for seeing the faint, extended glow of protoplanetary disks, the vast swirling rings of gas and dust where planets are actually being born. Sphere has provided some of the most breathtaking images of these cosmic nurseries, showing intricate gaps and spiral structures carved by unseen infant worlds. So while GPI excels at creating the ultimate dark, stable environment to watch giant planets dance, Sphere specializes in interrogating the faint light it captures, extracting every possible secret about the chemistry and physics of these alien worlds. Their landmark discoveries proved that direct imaging was no longer a theoretical dream, but a powerful operational science. They gave us our first family portrait of other solar systems, revealing a gallery of young, hot Jupiters in wide orbits, worlds that challenged our traditional models of how planetary systems form. They showed us that other suns could host planets in configurations unlike anything in our own familiar solar neighborhood, expanding our cosmic perspective forever. The moment of truth arrived not as a single point of light, but as a family portrait. In the constellation Pegasus, a star named HR 8789 revealed its stunning secret. It was not a solitary sun, but the heart of a solar system with 4 giant worlds, all seen directly for the first time. The images were breathtaking, a grainy yet profound collection of dots arranged around their central star. Here was a cosmic clockwork in motion, a complete planetary system captured by its own light. One by one, the planets appeared, 4 colossal gas giants, each one far more massive than Jupiter, tracing wide, stately orbits far from their sun. The public and scientific communities were electrified. This was not an artist's impression or a graph of data. These were real pictures. You could point to the screen and say, that is another world. That dot, that speck of light, is a planet. The images proved beyond any doubt that the extreme adaptive optics systems were not just engineering experiments. They were working telescopes capable of pulling entire families of planets from the stellar void. The grainy photos of HR 8789 were more than just pictures. They were a fundamental shift in our relationship with the cosmos. For the first time in human history, we were looking at alien worlds as actual places, their faint light finally separated from the glare of their star and captured by our cameras. The long-sought dream had become a tangible, undeniable reality. What new solar systems would emerge from the darkness now that we had finally learned how to see? Yet these spectacular images of distant gas giants were only the beginning. The true, ultimate prize remains a world like our own, a small, rocky planet orbiting within the habitable zone of its star. This is the new frontier for extreme adaptive optics, a challenge so immense it makes imaging a young Jupiter seem almost straightforward by comparison. The leap in sensitivity required is almost beyond comprehension. While a bright, young gas giant might be only 1,000,000 times fainter than its star, a true Earth twin would be nearly 10 billion times fainter. That is a difference of 4 more zeros, a factor of 10,000 times more difficult to detect. It is the difference between spotting a single candle next from a mile away and trying to see that same candle when it is placed right on the surface of the sun. To overcome this, every component of the system must be pushed far beyond its current limits. The deformable mirrors will need not thousands, but tens of thousands of actuators to create a zone of stillness so perfect that not a single photon of stray starlight pollutes the dark zone. The wavefront sensors will need to operate at speeds exceeding 10,000 corrections per second, and the computers processing that data will require power that rivals the world's most advanced supercomputers, all dedicated to this single, relentless task. New generations of coronagraphs are being designed with nanoscale precision. their spiral masks and intricate patterns etched to manipulate light with near-perfect efficiency. But the most radical solution might be to change the telescope itself. Future observatories plan to combine extreme adaptive optics with a starshade, a giant flower-shaped screen that would fly tens of thousands of kilometers in front of a space telescope, casting a perfectly deep, stable shadow and blocking the starlight before it even enters the instrument. This hybrid approach, marrying the best of space-based and ground-based technology, could finally provide the utter silence needed to hear the faintest whisper of light from another Earth. The race is on to build these next-generation instruments, to create a camera capable of seeing not just the giants of other solar systems, but the pale blue dots. When we finally capture that first grainy image, what will it tell us about our own place in the universe? These new giants of astronomy are already taking shape on remote mountaintops, their steel and glass skeletons rising to meet the sky. The next generation of telescopes, known as extremely large telescopes, will be colossal structures with light-gathering mirrors spanning over 30 meters. That is wider than a Boeing 737 is long. This is not just an incremental step up, it is a complete transformation of scale. The sheer amount of starlight these mirrors will collect is staggering, providing the raw signal needed to detect the faintest of cosmic whispers. But a mirror this vast also presents an unprecedented challenge for adaptive optics. The turbulence in the atmosphere over such a wide surface is more complex than anything we have ever had to correct. To tame this chaos, these telescopes are being built from the ground up with the most advanced extreme adaptive optics systems ever conceived, fully integrated into their very core. The deformable mirrors for these behemoths will be monumental feats of engineering, featuring not just thousands but tens of thousands of individual actuators, each one capable of microscopic adjustments at blinding speeds. They will be paired with laser guide star systems that project not one, but multiple artificial stars across a wide field of the sky, creating a three-dimensional map of the atmospheric turbulence above the entire telescope. The wavefront sensors and their controlling computers will operate at a scale and speed that pushes the very limits of modern computing, performing a real-time ballet of correction across an area of glass the size of a small building. What does this immense power buy us in the hunt for other worlds? It buys us the sensitivity to see not just gas giants, but smaller, cooler planets orbiting in the habitable zones of nearby stars. For the first time, we will be able to directly image rocky planets, super-Earths, and perhaps even Neptune-like worlds around Sun-like stars. The light collected from these planets will be far brighter and clearer than anything we can capture today. This torrent of photons will allow instruments like advanced coronagraphs to dissect the light with incredible precision, searching for the subtle chemical fingerprints of water vapor, methane, oxygen, and other potential biosignatures in their atmospheres. We will no longer just see these worlds as points of light. We will begin to study them as complex planetary systems. We could detect the presence of continents and oceans by observing how the brightness of the planet changes as it rotates, revealing the reflective properties of land and water. We might even be able to analyze the composition of their atmospheres over time, watching for seasonal changes that could hint at the presence of life. The Giant Magellan Telescope and the European Extremely Large Telescope are not just bigger telescopes, they are our generation's gateway to a new era of exploration. They are the machines being built to answer the oldest question, are we alone? By staring directly into the atmospheres of distant Earth-like worlds, they will search for the answer in the very light that touches them. While the ground-based giants push the limits of engineering, the ultimate solution to finding another Earth lies beyond our shimmering atmosphere. The vacuum of space offers a perfect, eternal stillness, a crystal-clear window free from the atmospheric turbulence that ground systems must constantly fight. It is here that NASA is planning its most ambitious observatory yet, a mission known as the Habitable Worlds Observatory. This is not merely a successor to the James Webb Space Telescope. It is a machine designed from inception for one singular, profound purpose: to directly image and analyze the atmospheres of at least 25 potentially habitable Earth-like worlds. Imagine the power of an extreme adaptive optics system, but one that operates in the perfect silence of space. Without an atmosphere to distort the light, the star's image is naturally stable and perfect. This allows the observatory's internal extreme AO system and its ultra-precise coronagraph to perform at a level of efficiency that is simply impossible on Earth. The system's deformable mirror, freed from correcting for atmospheric chatter, can focus its entire effort on creating a darkness of unparalleled purity around the target star. It can suppress the starlight with a stability and depth that ground telescopes can only dream of, carving out a deep, black well where the faintest of planetary glimmers can be seen. This is the key that unlocks the search for life itself. Once a rocky planet is isolated within this dark zone, the observatory will not just take its picture, it will capture its light and split it into a highly detailed spectrum. Scientists will then analyze this chemical fingerprint, searching for the subtle but telltale combinations of gases that could indicate a living world. The simultaneous presence of oxygen and methane, for instance, is a powerful potential biosignature. These gases react with each other and would quickly disappear from a planet's atmosphere unless they were being continuously replenished, most likely by biological processes. Finding such a balance on a temperate, rocky world would be one of the most profound discoveries in human history. The Habitable Worlds Observatory represents the culmination of every technological leap we have discussed, a space-based sentinel designed to stare into the light of other pale blue dots and answer the question we have asked for millennia. Are we alone? Its mission is to gather the evidence one photon at a time. This is the scientific payoff, the reason we have stretched our technology to its absolute limits. Once we have finally isolated the pale, reflected light of a distant Earth-like world, our work truly begins. We take that precious handful of photons and pass them through a prism, splitting them into a rainbow of colors, a spectrum. This is not for a pretty picture. A planetary spectrum is a chemical fingerprint, a unique barcode of light and dark lines that reveals the precise composition of the planet's atmosphere. Each gas leaves its own signature, absorbing specific colors of the starlight filtering through the alien air. Scientists will scan these barcodes with the intensity of a detective solving a cosmic mystery, searching for the telltale markers we call biosignatures. The most promising combination is the simultaneous presence of oxygen and methane. On a lifeless world, these two gases are arch-enemies. They react with each other and would vanish from the atmosphere in a short geological time. Finding them together in significant quantities is a powerful clue because life is a relentless, out-of-equilibrium process. On Earth, photosynthesis continuously pumps oxygen into our air, while biological processes like those in wetlands and the digestive systems of animals constantly release methane. Their persistent coexistence is a chemical signature written by life itself. Water vapor is another crucial piece of the puzzle, a sign of a world with the right temperature for liquid water to exist on its surface. But the search does not end with natural biology. The same techniques could, in theory, uncover something even more staggering: technosignatures. These are the chemical traces not of life but of an advanced civilization. Imagine detecting an atmosphere polluted with artificial refrigerants or industrial gases that have no known natural origin. Or perhaps we would observe unusual light patterns on the night side of the planet, the glow of vast cities illuminating the darkness. What if we were to detect a laser pulse or a structured radio signal deliberately aimed into the cosmos? The direct imaging of an exoplanet opens the door to this profound possibility. We are not just building a camera to find another Earth. We are building an instrument that could one day answer whether another intelligence is looking back at us, their own light silently crossing the void. The final frontier in this quest for cosmic vision is not just hardware but intelligence. The most advanced extreme adaptive optics systems are now integrating artificial intelligence, teaching themselves to see the universe with a clarity that surpasses even our most sophisticated programming. These are not simple automation tools, they are neural networks trained on vast libraries of atmospheric data and stellar behavior, learning to predict the chaos of our own atmosphere before it even happens. Imagine a system that does not just react to turbulence but anticipates it. By analyzing the subtle patterns in the wavefront sensor's data, an artificial intelligence can forecast how the air will distort the light in the next few milliseconds, allowing the deformable mirror to preemptively shape itself for a correction that is not just reactive but predictive. This shaves precious microseconds off the feedback loop, creating a deeper, more stable silence around the star. But the role of artificial intelligence goes even further, tackling the most insidious problem in direct imaging, the speckles. Even after the star's light is suppressed by the coronagraph, the image is not perfectly black. It is littered with a faint, speckled pattern, a residual glare caused by tiny, uncorrected imperfections in the optical system. To a human eye, or even a standard algorithm, these speckles look almost identical to the faint dot of a real planet. They are the ultimate cosmic imposters hiding in plain sight. This is where artificial intelligence becomes a master detective. By training neural networks on millions of simulated images, scientists teach them the subtle, telltale differences between a static speckle of starlight and the genuine signal of a planet. A real planet is a point source at an infinite distance, while a speckle is a fixed flaw in the optical train. As the telescope tracks the star across the sky, the speckles remain locked in place relative to the telescope's optics, but a real planet will move slightly in the field of view as the orientation of the solar system changes. An artificial intelligence can be trained to recognize this differential motion, this tiny, telltale drift that separates a ghost from a world. It learns to ignore the false positives and lock onto the true signal with unparalleled confidence, pushing the contrast limits into realms we once thought were physically impossible. This intelligent partnership between human ingenuity and machine learning is the next great leap. A system that not only creates a perfect silence but also learns to listen within it with a discerning ear, filtering out the universe's background noise to hear the one sound we are searching for, the faint, steady heartbeat of another world. For all its breathtaking power, this cosmic vision still has its blind spots. The system's ability to see clearly is utterly dependent on having a bright, nearby reference point, a guide star for its wavefront sensor to analyze. In regions of the sky where no sufficiently bright star exists, the system's eyes cannot focus, and its corrective vision fails. We can create artificial guide stars with lasers, but this only partially solves the problem, as the laser beam itself is distorted on its way up, limiting the fidelity of the correction. Another profound constraint is the narrow window through which we can peer. The exquisite correction of extreme adaptive optics is not panoramic. It creates a tiny, perfect island of clarity, often just a few seconds of arc across, centered tightly on the star. This is the equivalent of looking at the cosmos through a soda straw. While it is perfect for studying the immediate vicinity of a single star, it means we cannot take a wide-field, high-resolution image of an entire planetary system in one shot. We see the king, but we might miss the courtiers orbiting at wider distances. Perhaps the most insidious challenge comes not from our atmosphere or our instruments, but from the target system itself. Around many stars, including our own sun, there exists a vast cloud of warm, fine dust, the leftover debris from planet formation. This is exozodiacal dust. When we look toward another star, this dust reflects its light, creating a diffuse, glowing background, a cosmic fog that fills the very dark zone our coronagraph works so hard to create. Trying to spot an Earth-like planet in this environment is like trying to see a single, distant lighthouse through a thick, luminous haze. the faint light of the world we seek is lost in the collective glow of a trillion dust particles. These are not failures of engineering, but the fundamental physical boundaries we now confront. They remind us that every new window onto the universe comes with its own unique frame. But this quest for direct sight is not a solitary one. It thrives within a powerful, collaborative ecosystem of discovery, where different methods of finding planets work in concert, each revealing a piece of the puzzle that the others cannot see. The transit method, used by missions like the Transiting Exoplanet Survey Satellite, or TESS, watches for the telltale, periodic dimming of a star as a planet crosses directly in front of it. This gives us the planet's size, a physical measurement of its diameter. The radial velocity method, on the other hand, detects the subtle wobble of a star, pulled back and forth by the gravitational tug of an orbiting world. This provides the planet's mass, a measure of its gravitational heft. Alone, each technique offers a vital clue, but a limited one. A transit tells us how wide a planet is, but not what it is made of. A wobble tells us how heavy it is, but not if it has an atmosphere. This is where direct imaging with extreme adaptive optics enters the symphony. It provides the missing context, the visual proof. When we finally see that point of light, we can measure its brightness and its color. Combined with the mass from radial velocity, this brightness reveals the planet's density, telling us if it is a puffy gas giant or a dense, rocky world like Earth. Its color, when split into a spectrum, unveils the chemical makeup of its atmosphere, something the other methods struggle to achieve for planets in wide orbits. The true power emerges when we combine all these data streams. Imagine astronomers detecting a wobble, confirming a planet's mass. Then they watch for a transit, measuring its size and calculating a density that suggests a rocky composition. Finally, an extreme AO instrument like the Gemini planet imager turns toward that star, blocks its light, and directly captures the planet's own glow. The spectrum from that light could then confirm the presence of water vapor and the right temperature for liquid water, transforming a set of abstract measurements into a portrait of a potentially habitable world. This synergy is the future of exoplanet science. We are no longer relying on a single sense to understand these distant worlds. We are using every tool at our disposal, from feeling their gravitational pull and watching their shadows, to finally staring directly at their faint light, assembling a complete picture of alien solar systems, one shared discovery at a time. Creating this flawless cosmic vision requires engineering that borders on the impossible. The journey begins in a sterile cleanroom where the heart of the system, the deformable mirror, is born. Polishing its surface is not a matter of simple grinding, it is an act of atomic-scale sculpting. The mirror's face must be so perfectly smooth that any remaining imperfections are smaller than the wavelength of light itself. To understand that scale, if the mirror were expanded to the size of North America, the largest allowable bump would be less than the height of a single curb. Achieving this demands a process that combines chemical etching with ion beams, literally vaporizing stray atoms one by one to achieve a surface of almost unimaginable flatness. This is the foundation upon which everything else depends, a perfect canvas waiting for its thousands of microscopic actuators to bring it to life. But those actuators themselves are marvels of microengineering. Each one is a tiny, powerful piston, capable of moving with a precision of a fraction of a nanometer, a distance smaller than a single molecule of DNA. Assembling this intricate array is a ballet performed under powerful microscopes, where human hands are guided by robotic precision to place and bond each component into a perfect, functional whole. One misplaced element, one speck of dust, and the entire mirror's ability to correct light would be compromised, creating not clarity, but new and unpredictable distortions. Once this masterpiece of glass and micromotors is complete, the even more delicate task begins, the optical alignment. Every component in the extreme adaptive optics system, from the wavefront sensor to the coronagraph, must be positioned relative to the others with an accuracy that defies human perception. We are talking about alignments finer than 1/1,000,000th of a meter. The system is so sensitive that the heat from a technician's hand, or even the tiny expansion of metal from a shifting room temperature, can throw the entire assembly out of specification. To achieve this, engineers use lasers as their ultimate straightedge. They project a perfect laser beam through the optical path and watch for the most infinitesimal deviations. The process is one of agonizing patience, making microscopic adjustments, sometimes no more than a few atoms wide, then waiting hours for the entire system to thermally stabilize before measuring again. It is a painstaking dance of measure, adjust, and wait, repeated for weeks or even months until every element sings in perfect harmony. The moment of truth arrives when starlight first enters the aligned system. The engineers watch the wavefront sensors display, a frantic map of dancing dots representing atmospheric chaos. Then they engage the deformable mirror. In an instant, the frantic dance stops. The dots snap into a near-perfect, stable grid. It is the moment a chaotic blur becomes a perfect point, the moment a collection of exquisite parts becomes a single, unified eye capable of seeing across the galaxy. This grand achievement was never the work of a single nation or a solitary genius in a lab. The story of extreme adaptive optics is a testament to humanity itself, a global symphony of intellect and ambition. Universities from California to Paris, research institutes from Japan to Chile, and space agencies like NASA and the European Space Agency have all contributed vital pieces to this technological puzzle. No single entity possessed the full spectrum of expertise or the colossal financial resources required to build these cosmic cameras alone. The challenge was simply too vast. Instead, they forged a powerful international alliance, a shared dream that spanned continents. This collaborative spirit was not just beneficial, it was absolutely essential. The immense cost of developing and polishing those atomically smooth mirrors, or designing the algorithms that run 1,000 times a second, would have bankrupted any individual effort. By pooling funding and sharing the monumental risk, these global partners turned an impossible dream into a series of working instruments. Engineers in one country design the laser systems that create artificial guide stars, while scientists on another continent wrote the sophisticated code to interpret the data. The delicate glass for a coronagraph's vortex mask might be forged in Europe, painstakingly aligned in a North American cleanroom, and then installed on a telescope perched on a Chilean mountaintop. This was not a race with a single winner, but a shared journey of discovery. Every breakthrough in one lab was immediately communicated and built upon in another, accelerating the pace of innovation in a way that isolated competition never could. This global endeavor proves that the desire to see beyond our own world is a universal human trait, a collective yearning that transcends borders and unites us in the greatest search of all. The same technology that clears our view of the cosmos is now offering a clearer view of the human eye. The relentless pursuit of a perfect wavefront, born in giant observatories, has spun off into revolutionary tools for medicine. In laser eye surgery, the principles of extreme adaptive optics are creating procedures of unprecedented precision. Surgeons can now map the imperfections in a patient's eye with a detail that was once reserved for measuring starlight. This high-definition map allows the laser to sculpt the cornea with microscopic accuracy, not just correcting basic vision problems like nearsightedness, but also tackling subtle, higher-order aberrations that cause halos and starbursts around lights at night. The result is vision that can potentially become sharper than 20/20, a clarity that feels almost superhuman. This is not just about removing glasses, it is about achieving optical perfection for the human eye, using the same physics that lets us see planets light years away. That same quest for a perfect image is also transforming how we look inside the body. Advanced retinal imaging, inspired by these astronomical systems, can now peer into the living eye with cellular resolution. Think of an extreme adaptive optics system applied to a medical camera. It uses a deformable mirror and a wavefront sensor to measure and cancel out the distortions caused by the eye's own lens and fluids. This correction creates a crystal-clear view, allowing doctors to see individual photoreceptor cells and blood cells moving through the finest capillaries in the retina. They can watch these cells in real time, detecting the earliest signs of diseases like macular degeneration or diabetic retinopathy long before permanent vision loss occurs. It is like having a satellite image of a landscape, but for the delicate tissue at the back of your eye, enabling early intervention that can save a person's sight. Beyond the doctor's office, the ripple effects reach the heart of modern technology, the semiconductor foundry. The process of etching intricate circuits onto silicon chips requires projecting incredibly detailed patterns of light through a mask, much like a coronagraph creates a precise shadow. Any tiny imperfection in the optical system, any vibration or thermal drift, will blur the pattern and ruin the microscopic transistors. The vibration damping systems and nanometer-stable positioning technologies developed for extreme adaptive optics, where a jitter of 1/1,000,000th of a meter is catastrophic, are now essential for the next generation of chip-making machines. This ensures that the light used to print circuits is as steady and perfectly controlled as the light from a corrected star, allowing us to build faster, smaller, and more powerful computers. The journey to see another Earth is quietly fueling the devices we use every single day. What other hidden connections between the cosmos and our daily lives are waiting to be discovered? The timeline of this cosmic vision began not with a telescope but with a thought. In the 1980s, the idea of directly photographing an exoplanet was a fringe concept, a theoretical proposal sketched out in scientific papers. There were no instruments capable of such a feat, only a handful of visionaries who dared to calculate the staggering engineering hurdles. They laid the intellectual groundwork, defining the problem of contrast and angular separation that would need to be solved. The 1990s and early 2000s became the era of foundational technology, a period of intense laboratory experimentation. This was when the core components of adaptive optics and coronagraphy were pushed from academic curiosities into sophisticated prototypes. Scientists built their first deformable mirrors with a few dozen actuators and tested primitive coronagraphs, proving in controlled environments that starlight suppression was physically possible. Each small success in the lab was a brick laid on the path to the stars. The breakthrough arrived in the mid-2000s, a golden age of first light. The Gemini planet imager and the Sphere instrument saw their first photons, moving from blueprints on a desk to operational instruments on the world's most powerful telescopes. Their launch marked the moment direct imaging transitioned from a daring experiment into a legitimate, productive science. They delivered the first family portraits of alien worlds, proving the technology could work outside the sterile confines of a laboratory. We are living in the present era of rapid discovery and refinement. These pioneering instruments continue to survey the skies, discovering new worlds and refining their techniques with every observation. Simultaneously, the colossal mirrors of the extremely large telescopes are being cast and polished, their construction representing the next great leap. Their immense light-gathering power, combined with even more advanced extreme AO systems, will define this decade, allowing us to image smaller, cooler planets than ever before. The future is already taking shape on drawing boards and in conference rooms. The 2030s and beyond point toward the ultimate goal, the launch of the Habitable Worlds Observatory. This space-based marvel will combine all the hard-won lessons from decades of ground-based innovation, operating in the perfect silence of orbit to achieve the final, profound step, the direct imaging and atmospheric analysis of an Earth-like world around a Sun-like star. This entire timeline, from a speculative idea to a mission designed to find life, has been compressed into a mere half-century, a breathtakingly short sprint in humanity's long quest to understand the cosmos. What seemed impossible a generation ago is now a matter of when, not if. These first direct images of alien worlds did more than fill scientific journals. They ignited a global conversation. A grainy, orange dot against the blackness of space became a shared cultural touchstone, a tangible piece of evidence that the universe is teeming with other solar systems. This visual proof, more than any graph or data set, has a unique power to capture the human spirit. It transforms abstract concepts into real places, inviting everyone to share in the wonder of discovery. To harness this collective curiosity, scientists have opened the doors of their research, creating projects that allow anyone with an internet connection to join the hunt for new worlds. These citizen science initiatives recognize a powerful truth that the human brain, with its incredible pattern recognition skills, can sometimes spot what even the most sophisticated algorithms might miss. One such project invites volunteers to sift through the treasure trove of data from direct imaging surveys, examining processed images of distant stars. The task is to look for that faint, telltale speck of light that could be a new planet. You are presented with an image where the central star has been artificially dimmed by the coronagraph, leaving behind a dark field that should be empty. But scattered across that darkness are residual speckles and noise, the cosmic imposters that can mimic a planet's signal. Your job is to click on anything that looks like a genuine, point-like source. Is that a stable, bright pixel that appears in multiple images taken at different times, or is it just a random fluctuation? This collaborative filtering process, with thousands of eyes scrutinizing the same patch of sky, creates a powerful consensus that helps professional astronomers prioritize their most promising targets for follow-up observations. The impact of this public engagement extends far beyond data processing. Online forums and social media groups have blossomed into vibrant communities where amateur astronomers, students, and space enthusiasts dissect new findings, share their own observations of variable stars, and discuss the latest technological breakthroughs. A high school teacher in Brazil might be guiding her students through an analysis of an exoplanet spectrum, while a retired engineer in Japan uses his free time to help classify potential planetary candidates. This global network of curious minds forms a distributed brain, all focused on the same profound questions. By participating, people are not just passive consumers of science, they are active contributors to one of humanity's greatest adventures. This shared endeavor reminds us that the quest to understand our place in the cosmos is a journey we are all on together, each pair of eyes adding to our collective vision. These first portraits of alien worlds do more than satisfy scientific curiosity. They ripple through our global economy. The relentless engineering demands of extreme adaptive optics have created a surge in high-tech job markets, from optical engineers and laser specialists to the software developers writing the complex code that powers these systems. This is not a niche field, it is a catalyst for innovation that spills over into countless other industries. The techniques perfected for polishing atomically smooth mirrors are now used to create flawless lenses for medical scanners and high-end cameras. The vibration damping systems that keep a telescope perfectly steady have been adapted for use in semiconductor manufacturing, where even a microscopic tremor can ruin a billion-dollar batch of computer chips. This technological ecosystem supports a vast network of suppliers, manufacturers, and researchers, fueling an economic engine driven by the most fundamental human desire to explore. But the true value extends far beyond balance sheets and job reports. When we finally capture that first clear image of a pale blue dot orbiting another star, it will trigger a philosophical shift as profound as the one Copernicus began centuries ago. For all of human history, our place in the cosmos has been a matter of speculation and faith. We have wondered if we are alone, if other Earths exist, but we have never had the evidence to answer that question directly. That is about to change. The knowledge that we are building machines capable of seeing potential sister Earths recontextualizes our entire existence. It moves the question of life elsewhere from the realm of philosophy and fiction into the domain of observable, testable science. We are no longer passive inhabitants of a single world, gazing at distant points of light and wondering. We are becoming cosmic cartographers, actively mapping the archipelagos of other solar systems. What happens to our sense of self when we can point to an image and say, that is not a star, that is a sun, and circling it is another world that may hold oceans, continents, and perhaps, just perhaps, a consciousness looking back at us across the void? That single pixel of light is a universe of information in disguise. It is crucial to understand what these historic first images truly represent, and perhaps more importantly, what they do not. The stunning artist's impressions of swirling blue marbles and craggy continents are just that, artistic interpretations. The raw data from even our most advanced instruments today is far more humble, yet in its own way far more profound. We are not looking at a detailed photograph of an alien world. We are collecting a single, tiny point of light, often just one pixel on a massive detector. This is not a failure of our technology, but a testament to the staggering distances involved. From dozens of light years away, an entire planet, even a gas giant, is simply too small to resolve as a disk. It remains a solitary speck against the void, but within that single speck lies everything. That pixel is not just a measure of brightness, it is a container for a spectrum, a rainbow of colors encoded with the chemical secrets of a world light years away. We take that pixel and split its light apart, reading the dark and bright lines that act as a unique barcode for the gases in that planet's atmosphere. From one point of light, we can deduce temperature, composition, the presence of clouds, and even the force of its winds. We are not seeing the planet's surface, we are reading its vital signs. This means that for the foreseeable future, we will not be glimpsing alien coastlines or the glittering lights of cities on the night side. The leap from analyzing a planet's atmospheric barcode to resolving surface features is monumental. It would require a telescope so vast its mirror would need to be measured in kilometers, not meters, an endeavor that belongs to a future we can scarcely envision. The true wonder is not in what we cannot yet see, but in the breathtaking amount we can learn from a single, silent point of light. We have crossed a threshold that once existed only in fiction, transforming the dream of seeing alien worlds into a breathtaking scientific reality. This journey into light, from the shimmering chaos of our atmosphere to the profound stillness carved by deformable mirrors, has given us a new sense. We can now look upon planets not as data points, but as actual places, their faint light finally separated from the glare of their suns. The path ahead remains steep, pushing against the very limits of engineering and physics to find that one pale blue dot orbiting a distant star. Yet the potential reward fuels this entire endeavor, the chance to find the first definitive evidence that we are not alone in the cosmos. Every photon gathered, every speck of light analyzed, brings us closer to an answer that would redefine humanity's place in the universe. The future of exploration is being written now, in the silent language of light traveling for decades from distant suns to our waiting cameras. It is a story we are all a part of, a collective step into a larger, more wondrous cosmos. If you could choose, which of these newly discovered worlds would you want to see up close first? Let us know in the comments, and if this journey has inspired you, be sure to like and subscribe for more voyages to the frontiers of discovery.